Ladies and gentlemen, welcome. This is again 4ST601, Statistics in English, and our seminar number 12. If you remember, on the last seminar we finished with hypothesis testing, and today we will continue. If you remember, we already seen this example before, yes, and I said a few weeks ago, yes, that I will return to this example one more time. There is a table, a contingency table with absolute frequencies about the development of disease and the question if the patient was vaccinated against some disease. Yes, we recalculated this table, yes, empirical table to theoretical table. Table is theoretical expected frequencies. We calculated the value of G. We did not know what is it G, yes, but according to this value G, we calculated the measure of dependence, the characteristic of existing dependency, Pearson coefficient C and Kremer coefficient V. Yes, that's all. It was a descriptive way. And today we will return to this example, and the question: does the development of the disease depend on whether the patient was vaccinated? This question will be tested, as statistically tested on the alpha 5% significance level. We know that there is a dependence, yes. We measured this dependence by coefficients, Pearson and Kremer, but today we will run the statistical hypothesis test. So I will very fastly recalculate this table one more time to expected table of expected theoretical frequencies. Yes, and according to value of G, I will test the hypothesis. Where is our hypothesis? In formulas, you can find this table, contingency table, rows times columns, large sample, and our zero hypothesis. Variables are independent. Yes, so there is independence in the table. Yes, alternative hypothesis, non-A0 dependence. Yes, variables are dependent. So I will calculate the value of the statistic G, and after I will use this rejection region, because the value of G can be element either of region of acceptance or a rejection region. Yes, if statistic G is element of rejection region, zero hypothesis is rejected at a 5% significance level. Yes, so I will return on the whiteboard, yes, and I will recalculate the table with empirical frequencies to expected theoretical frequencies very fastly. Okay, so there is rewriting the table, mild and hard development, and yes or no, the patient was vaccinated. Yes. Okay, so we know according to this table that M sample size is equal to 93. You remember that we need to calculate here the marginal frequencies. So this is very fast recapitulation of what we already know. Yes. Okay, so M, E, J with stripe, mild and hard, yes or no. So another table will be here. Perfect. So very fastly, marginal frequencies, the side frequencies, 33 plus 9, yes, 42, 15 plus 36, 51, 33 plus 15, 48, 9 plus 36, 45. Okay, so we will calculate these frequencies. 42 times 48, yes, because there is n e dot times n dot j divided by n. Yes. Okay, so here 42 multiplication 48 divided by 93 patient 21.68. 21.68. Another value 42 and 45. 42 times 45 divided by 93. 20.32. 20.32. And we can continue 51 and 48. 51 times 48 divided by 93. 26.32. 26.32. And finally 51 times 45 divided by 93. 24.68. 24.68. Table with expected frequencies. Empirical frequencies, expected frequencies. The value of G. The value of G will be calculated like N E J minus N E J with stripe. This must be in squares divided by N E J with stripe. Yes, and don't forget that this is summation. There must be summation sigma and one more summation, one more sigma, because it's a summation through all rows and all columns. So the value of G is equal to this, and I will use this part on the whiteboard, and 33 minus 21.68 squared divided by 21.68, yes, plus, and I will finish this here, 9 minus 20.32 squared divided by 20.32 plus 15 minus 26.32 squared divided by 26.32, and finally 36 minus 24.68 squared divided by 24.68. Yes. Okay, so the partial results will be written, for example, here G is equal to 33 minus 21.68 squared divided by 21.68, 5.91. 5.91 plus 9 minus 20.32 squared divided by 20.32, 6.31, 6.31 plus 15 minus 26.32 squared divided by 26.32, 4.87. 4.87 plus finally 36 minus 24.68 squared divided by 24.68, 5.19. 5.19. Okay, I don't need this anymore, yes? So this can be deleted. Okay, wait a second. And the value of G is equal to, this will be test statistic. Yes, test statistic will be written here, the value of the test statistic. Yes, calculated value. Okay, 5.91 plus 6.31 plus 4.87 plus 5.19, 22.28. Okay, you already seen this value, yes? This value of G. And now we must return back to the table in your formulas, where we had set the zero and alternative hypothesis. H0 claims the variables are independent, yes? So independence, yes? Independence is zero hypothesis every time. Do you remember our last example on our last seminar about the fair dice? We had a fair dice, yes? And at the end of our seminar, I talked about chewing gum, yes, placed on one side of the dice, yes? And the last statistical hypothesis test, yes, which was used on the previous seminar, was chi-square goodness of fit test. It was a test designed on testing of frequencies, yes? Frequencies, absolute or relative frequencies. And this hypothesis test, yes, is also designed on the testing of frequencies, yes? If N, E, J is equal to N, E, J with stripe, it's independent, yes? If this value is equal to this value, if this value is equal to this value, if this value is equal to this value, etc. Yes? This is designed on the testing of frequencies, and if there is a significant difference at 0.05% level, 5% significance level, yes? Zero hypothesis is rejected and the valid is alternative one, dependence, yes? H1 is dependence. Dependence is alternative hypothesis, yes? And there is a very important thing, the rejection region. W alpha, yes? Okay, so W alpha for the statistic G is valid. If statistic G, the value of statistic G is higher or equal to critical quantile chi-square 1 minus alpha %, we enter to the rejection region and we must reject the zero hypothesis on this 5% significance level. Very important is that chi-square distribution, we are searching for chi-square quantile 1 minus 5% is 0.95%. We must searching for this critical value, critical quantile, yes? Critical value, yes? Critical value is this quantile with degrees of freedom ni. This is small Greek letter ni, which is equal to number of rows minus 1 times number of columns minus 1. Yes? Do you know how many rows and columns we have? We have 2 rows and 2 columns. Yes? So the calculation of degrees of freedom ni is 2 minus 1 times 2 minus 1, this is equal to 1, so we will use degrees of freedom ni equal to 1, and we are searching for chi-square quantile 0.95 with degrees of freedom ni equal to 1. So please try for me to find this critical quantile. Do you know where you have quantiles of distribution chi squared? I will check the board next to this whiteboard, yes? So where I have a table here, it's a table 5, yes? Table 5. Please find 95% quantiles in table 5 and 1 degree of freedom. It means that it will be the first row. And try to find value 3.84. Yes, 3.84. Okay. The value of G22 is higher than this critical quantile, so this inequality is true. Therefore, you entered to the rejection region, and because the statistic is element of rejection region, at the 5% significance level is rejected zero hypothesis. Zero hypothesis about independence. It's rejected at the 5% significance level. It means that it statistically depends. It depends, yes, whether the patient was vaccinated on the development of the disease, yes. Few weeks ago, we calculated the value of Pearson coefficient C as the measure of existing dependency and the value of Kramer coefficient V. Yes? So, in any cases, if zero hypothesis is or is not rejected, yes, you can calculate the strength of this dependence, yes? We already calculated this strength of the dependence, yes? So, if you don't remember, yes, watch some of the previous seminar, yes, where we had a descriptive way of contingency tables analysis. Okay, so contingency tables analysis and hypothesis test of dependence. Yes, this is very powerful tool necessary, for example, to your bachelor or diploma thesis. Yes, if you perform some survey with questions. Yes, survey questions, for example, for respondents, yes, these tables are very useful, and hypothesis testing is also very useful. So I will return one more time, yes, to our well-known example about the speed of the reaction and the level of alcohol in blood. Yes, we talked that in many countries in the world, yes, it's prohibited to drink before the driving, yes. And we already calculated Pearson coefficient C and Kramer coefficient V, which was, I don't know, 0.67, 0.68. So we could expect, yes, that there is a dependence, yes, dependence between the speed of the reaction in car, yes, and the level of alcohol in blood. Yes. And today, again, we will test the hypothesis which claims independence. Yes, it's independence between the speed of the reaction and the level of alcohol in blood. We can expect that there is dependence. Yes, so you can expect that probably we will reject zero hypothesis. Yes, but we will calculate it. Yes, I will show you the proof that zero hypothesis will be probably at the 5% significance level rejected. Yes, but before I will show you from the previous examples. Yes, can you see quantiles of the chi-square distribution? There you can see p value 0.95. And the first value here, 3.84, was quantile for degrees of freedom 1 degree of freedom, yes? Today, or now we have a table with dimension 3 times 2. Yes, 3 times 2. And degrees of freedom is calculated like 3 minus 1 times 2 minus 1. Number of rows minus 1 times number of columns minus 1. So 3 minus 1 times 2 minus 1 is equal to 2. So we can check our tables and you can see that for 2 degrees of freedom will be 99% quantile equal to 5.99. So if our value of G is higher than 5.99, zero hypothesis will be rejected at the 5% significance level. Okay, so as I already said, there is a table with our well-known empirical absolute frequencies, yes, NEJ and NE dot and N dot J are our marginal frequencies, yes, marginal frequencies, the side frequencies calculated on the side of the table, yes, 53 plus 12, 63, 65, yes, 5 and 15, 20, 2 and 13, 15, yes. Do you remember 100 drinking drivers, yes? 65 and 5 is 70, 80 and 20 is 100. Okay, 53 and 2 is 55 and 5 is 60. So 60 drivers here and 40 should be here, yes? 12 plus 15 plus 30, 40. Okay, the table NEJ with stripe, yes? Good reaction, bad reaction, low, middle and high. So, okay, we will create the table here. And the recalculation is very easy. NE dot times N dot J divided by N. Yes, so 65 and 60. 65 times 60 divided by 100. 39 drivers. 39 drivers. 65 times 40 divided by 100. 26 drivers. 20 and 60. 20 times 60 divided by 100. 12 drivers. 20 and 40. 20 times 40 divided by 100. 8. 15 and 60. 15 times 60 divided by 100. 9. And here finally 15 times 40 divided by 100. 6. Okay, table with independent frequencies, expected frequencies, theoretical frequencies, yes? How the situation will look like if there will be independence. Independence between the level of alcohol in the blood and the speed of the reaction. So, zero hypothesis is, for example, NEJ is equal to NEJ with stripe for all E and all J, yes? For all E and all J. So this is independence. Yes, independence. Okay, so this is our zero hypothesis, and we need to calculate G. And G will be calculated like 53 minus 39 squared divided by 39 plus 12 minus 26 squared divided by 26 plus 5 minus 12 squared divided by 12 plus 15 minus 8 squared divided by 8 plus 2 minus 9 squared divided by 9 plus 13 minus 6 squared divided by 6. Yes, we already calculated this, so this is only recapitulation. Yeah? This is the reason why I calculated so fast. So 53 minus 39 squared divided by 39, 5.03. So G is equal to 5.03 plus 12 minus 26 squared divided by 26, 7.54. 7.54 plus 5 minus 12 squared divided by 12, 4.08, 4.08 plus 15 minus 8 squared divided by 8, 6.13, 6.13, 1, 2, 3, 4, 5, 2 minus 9 squared divided by 9, 5.44, and finally the last value 13 minus 6 squared divided by 6, 8.17, 8.17. Okay, so the value of G will be here 5.03 plus 7.54 plus 4.09 plus 6.13 plus 5.44 plus 8.17. I will use only one decimal, 36.4, because you already expect, yes, that this hypothesis will be rejected. Why? Because W alpha is equal to 4 statistic G is valid. If G, the value of G is higher or equal to critical quantile He squared, yes, 1 minus alpha with degrees of freedom Ni, 1 minus alpha with degrees of freedom Ni, yes, we enter to the rejection region and zero hypothesis is rejected. So we know that this quantile He squared 0.95, 95% quantile with degrees of freedom equal to 2. So this quantile was 5.99. So this is the critical value. And if G is higher or equal to critical value, yes, we enter to the rejection region and zero hypothesis is rejected. 36 is higher than 6, 5.99. So this hypothesis about independence, yes, is rejected at the 5% significance level. Statistically, it depends. Yes, it depends the speed of the reaction in car, yes, on the level of alcohol in blood, it depends, yes. So again, like in case of previous example, if you want, you can calculate one more time the Pearson C and Kramer V for the characteristic of the strength, yes, of this dependence, because we already know that it depends. Okay. Okay, so there is another well-known example for us, yes? We observed 12 students, how many points they got from the final test, for example from statistics, because that is the range from 0 to 60. We know that 4 of the students were always attend the classes of one of the 3 teachers, Mr. McDonald, Mr. King and Mr. Benz. And there is a question, has the person of the teacher the influence on the number of achieved points from the final test? We already calculated effect size, yes? Effect size on the basis of calculated sum of squares, yes? And this effect size, the strength of the dependence of the teacher, yes, on the number of achieved points, yes, was calculated. I don't remember if we calculated 0.68, 0.69, I don't remember, yes, maybe at the end of this example I will calculate effect size one more time. But before, we will solve this example one more time, but today in Excel, because we have here very nice table ready for Excel calculation. And we will decide on alpha 5% significance level if there is this dependence really statistically significant, yes? So we will run the statistical hypothesis test in the case of ANOVA, analysis of variance. So we will check our formulas. So where we have formulas here, analysis of variance. This important table, yes? Please check 0 and alternative hypothesis. 0 hypothesis claims mu1 is equal to mu2, this is equal to mu3, mu4, mu5, etc. until mu k, yes? So 0 hypothesis claims equality of at least 3 means. At least 3 means. This method is designed, yes, for using on at least 3 groups. We have a group of Mr. McDonald, Mr. King and Mr. Benz, yes? So 3 teachers, 3 groups, it's enough. At least 3 means, yes? Equality of 3 means. Can you see this label? Analysis of variance. Analysis of variance, yes? Why this method is called analysis of variance? When 0 hypothesis claims equality of at least 3 means, averages. Why? If you don't know the answer, wait about 10 minutes, yes? And at the end, I will say this for you, yes? So, why is this method called analysis of variance if 0 hypothesis is designed, yes, on equality of at least 3 means? This will be responded at the end. So, we can say at the beginning that this 0 hypothesis claims independence again, yes? There is an independence, yes? Independence between a number of achieved points and the teacher, the factor of teacher, yes? So there is no influence of the teacher on the number of achieved points. Independence, again, yes? 0 hypothesis is independence every time. Alternative hypothesis, in at least one case, the mu, the average achieved points, yes, is different in comparison with other ones, yes. So it means dependence. There is a dependence of the teacher, yes, on the number of achieved points. So what we need to calculate test statistic, Fisher F statistic, yes, and the value of this Fisher F statistic is calculated like this nominator divided by this denominator, and in the numerator you can find as sum of squares, TR, treatment. Yes? Do you remember where I calculated treatment sum of squares for you? Yes? Divided by k minus 1. K is number of teachers, number of groups, 3 minus 1. Yes? And E is error. Sum of squares, error, sum of squares, divided by n minus k. Do you remember? I calculated error sum of squares for you like a bonus. Do you remember the situation? I will scroll up. Yes, I will scroll up where you can find. It's many weeks ago, please wait a second, really many weeks ago, regression, correlation, analysis of variance. It was, I don't know which one, third week, fourth week of our academic semester, yes, effect size, treatment, sum of squares, divided by total sum of squares. And because we did not, there was not necessary for calculation of error sum of squares, I showed to you error sum of squares like a bonus. So we know how to solve this manually, yes? The large example on the whiteboard. So now we will return to this example. We will calculate treatment and error sum of squares in Excel. Yes, we will find the degrees of freedom. Degrees of freedom, because this is Ni1 and this is Ni2. Yes, sum of squares treatment divided by Ni1. Ni1 is parameter of Fisher distribution. N minus k is Ni2, small Greek letter Ni2, N minus k. So second parameter of Fisher distribution, yes. And again, because there is zero hypothesis, there is value of the statistic, and this value of the statistic can be element of rejection region. And this is true in the case that Fisher statistic is higher or equal to critical quantile from the tables, from the Fisher distribution tables, and quantile F1 minus alpha. There was probably written that we should use alpha 5% significance level, okay? So we will do this. And your Fisher tables are here. So please wait a second. There is student distribution. Yes, the last table, your last table, you can see quantiles F0.95 of the F distribution of Mr. Fisher. So Ni1 and Ni2 we have here. So we will solve our example in Excel, and after we will try to find the quantile. Okay, so there is Excel, yes. And if you remember, on data leave, we already installed a special add-in, yes? But because I did not use this add-in in this classroom many weeks, yes, it's deleted, so I will install this add-in here back to Excel, yes? So, please, you can click on File button, and here on the bottom, yes, you can find options. So please click on options, yes, and you will see this large table where we can find add-ins. Click on add-ins, and here on the bottom you will see manage Excel add-ins, yes, and there will be go button with 3 dots. Go button with 3 dots. You will select this go button with 3 dots, And here in this small table, you will select Analysis Toolpath, click on OK, and on in the right top corner of the data leaf, you will see Data Analysis. So please switch on Data Analysis, Analysis Toolpath, OK, and now within a few seconds, you will see here Data Analysis, and we will find here something what is called ANOVA. ANOVA single factor. ANOVA single factor because we have here only one factor, and this factor is teacher. Teacher, yes. The influence is teacher, yes, on the number of achieved points. Okay, so ANOVA single factor, you will see that it's very easy. Input range, yes. Input range, I will select these three columns, number 1, number 2, number 3, and the values. Yes, so this is my input range, grouped by columns, yes, because I have this grouped by columns, and alpha is 0.055% significance level. Very important, I have labels in first row. I also selected number 1, number 2, number 3. So I have labels in first row, and that's all. I can click on OK, and you will see result here. Yes. So I will zoom this document. Okay. So yes, that's all. Nothing more is here. Okay. So maybe if you remember how we solved this example many weeks ago, you can find here individual averages. Yes, for example, here in summary table. Group number 1, number 2, number 3, yes, 4 students in each group, yes, and we calculated individual averages for each teacher, yes. And if you remember our zero hypothesis, yes, our zero hypothesis is that average number of achieved points in a group of Mr. McDonald is equal to average number to achieved points in the group of Mr. King, yes, and this is equal to average number of achieved points in the case of group Mr. Benz, yes. So Mr. McDonald, King, and Benz are equal, yes, equal teachers. And you can see here that we have here differences, yes, differences. The last teacher, number 3, has the smallest result. Mr. McDonald has the largest result, but we would like to test this at the 5% significance level. So we have here ANOVA table, and it will be good to write here something more. Source of variability, yes. Between groups, this is treatment variation. Treatment variation, yes, I will use where I have merge okay, so there is wrap text, yes, so between groups is treatment variation. Within groups will be error variation, yes, so between groups treatment variation, wait a second, okay, and there will be within groups equal sign error variation, error source of variation, yes. Okay, and there we have total. Total is total. So, do you remember when I calculated for you sum of squares? Sum of squares, this is here, yes, sum of squares, we have here SS, sum of squares, treatment, sum of squares, error, sum of squares, and total sum of squares, yes. We only calculated effect size, yes, effect size, ES. I will calculate your effect size, for example here, effect size, if you remember, was equal to ratio sum of squares, TR, treatment, divided by sum of squares, total, yes, sum of squares, treatment, divided by sum of squares, total. And we calculated treatment divided by total sum of squares. Yes, and do you remember the result? I don't remember. So I will see. 0.628. Yes, 0.628 was our calculated effect size. Yes, so we could expect, yes, that there is a dependence between number of achieved points from the final test and the factor of teacher, yes. So now we will test this as the statistical dependence. So we know what is it, sum of squares, it's here, df, degrees of freedom, yes, degrees of freedom, degrees of freedom. So there we have our values Ni1 and Ni2. Yes, you can see 2 and 9. Degrees of freedom Ni1 and Ni2. So parameter of Fisher distribution. Ni1 is calculated like k minus 1. How many teachers we have? Minus 1, 2. Yes, so we have 2 degrees of freedom Ni1 and n minus k. How many students we have? 4 plus 4 plus 4. 12 together. Yes, 12 students minus k, number of teachers, 3. 12 minus 3 is equal to 9. Yes? So 2 and 9 degrees of freedom. And you can verify that we have here calculated 2 and 9. Yes? So we already know what is it, degrees of freedom. We need these 3 values. And in the case of degrees of freedom, we need these 2 values. Yes? This summation 11 is useless, yes, we don't need this for anything. Mean squares. What is it, mean squares? Yes, there is mean squares. The mean calculated from squares. Yes, you can see that there is value 90.58 and 11.94. Mean square is a variance. Why? Because it's a mean calculated from sum of squares. Yes? Do you remember the formula for the calculation of variance? Summation of squared differences between the values and arithmetical mean, and this was divided by number of observation. In the case of ANOVA, this mean square is calculated like sum of squares, the sum of squared differences, yes, square differences between the values and arithmetical mean, divided by something, divided by degrees of freedom, divided by k minus 1. And this second one, this second mean square, can be called error variance. The first one can be called treatment variance. This second one, error variance. Because it's a sum of squares, error, sum of squares, divided by something, divided by degrees of freedom, df, for error source of variation. So you can verify that I can delete these two values and calculate here this value divided by this value, and you will see the same result here. And of course here this value divided by this value, yes, and you will see the same result here, yes. So I do this, enter, and here this value divided by 9, and you can see that we have here the same variances. This is very important. This is treatment variance and error variance. And finally, if you check these formulas, you can see that value of test statistic, yes, is calculated like ratio. Treatment sum of squares divided by k minus 1. In our situation, treatment sum of squares divided by 2. In denominator, we have error sum of squares divided by n minus k divided by degrees of freedom equal to 9. Yes. So the ratio of two variances, the ratio of treatment and error variance, is value of f statistic. So again, you can verify that this Fisher f statistic, which is equal to 7.58, yes, if you delete this value and calculate here ratio of these two variances, you will see this f statistic, f test statistic, yes. So you can click on enter, yes, and you can see that there is the same value. So this is f value of Fisher f statistic. Okay, so this is the most important for you, and we can finish this example using our statistical tables, for example. Yes, because according to formulas, you can see that if Fisher f statistic 7.58 is higher than critical value f1 minus alpha, we will enter to rejection region, and this hypothesis is rejected. So we will search for 95% quantile of Fisher distribution with how many degrees of freedom? Me1 and Me2, 2 and 9. 2 and 9 degrees of freedom. So please check the tables, check statistical tables. Me1 is equal to 2 and Me2 is equal to 9. Yes, so please, 2 and 9 degrees of freedom, and there you can see the result. 4.257. 4.257. We will return back. Yes, we will return back to Excel, and here you can find critical value. There is small difference on the last decimal, but it's all right. Yes, so there is a value and there is critical value. Fisher f statistic f value and critical value is here. So you can see that we have everything calculated and everything written in Excel. If your f statistic is higher than this critical value, zero hypothesis is rejected at the 5% significance level. Yes, and it's true. There it's true. F statistic is higher. We enter to the rejection region. Zero hypothesis is rejected. Zero hypothesis was independence. Yes, independence. So it depends. Yes, it depends. you can see that we already calculated here effect size, like a ratio sum of squares treatment and the sum of squares total. Yes, so we know that effect size, yes, is from range 0 and 1, and if this effect size is closer to 1, there is a stronger dependence. Yes, okay. Maybe one note to this p-value. Yes, this is also useful for you. This p-value. It's a probability. Yes, and this p-value says to you information about the significance of the test. Yes, if this p-value is higher than 5% significance level, yes, the zero hypothesis is not rejected at the 5% significance level. So, one more time, please. If this p-value, yes, is higher than 5% significance level, it's not true now because it's 1%, yes, but if this will be higher than 5%, so at the 5% significance level, the zero hypothesis is not rejected. But because this is below 5% significance level, zero hypothesis is rejected at the 5% significance level. So either we can p-value or we need critical quantile. Yes? At least one of this information is necessary for us. In formulas, you don't have formula for the calculation of p-value. Yes? P-value is calculated in software. If I delete this p-value, yes, if I delete this p-value from this table, you don't have any other option only to find critical quantile. Yes? So we know that we must either find critical value and compare F statistic and critical value, or we have p-value and we can decide one more time. If this p-value is above 5% significance level, zero hypothesis is not rejected at the 5% significance level, because this is below 5% significance level. At the 5% significance level, zero hypothesis is rejected. Yes, so that's all. Do you remember our example about consumption using 3 types of petrol? We analyzed, for example, consumption of petrol from petrol station Shell, Ajib and OMV. Yes. So 3 types of petrol using experiment. There were done 5 experiments with each petrol. We will fill the ANOVA table and we will try to decide on alpha 5% significance level whether the consumption depends on the type of petrol. If you remember, we had here calculated sum of squares total, yes, and sum of squares error. There is another one source of variation between groups, which can be called model or which can be called treatment. Yeah? So I will write it here. Treatment, error and total. Yeah? So we have calculated only sum of squares, and the rest of information is written in the sentences in this example. Yes, 3 types of petrol, 5 experiments with each petrol. So 3 times 5 is equal to 15, and 15 will be the total number of observation and the sample size. Yes, the sample size will be equal to 15, and because we have 3 types of petrol, it's the same like in the case of previous example where we have 3 teachers. So we have here 3 groups, Shell, Ajib and OMV, for example. Yes, 3 types of petrol. and 15 experiments in total. We will use alpha 5% significance level, and we will run the hypothesis test, where will be mu1 equal to mu2 will be equal to mu3. Average consumption of shell is equal to average consumption of AGIP, and this is equal to average consumption of OMV. It means independence. There is no dependence, yes? If you use petrol from Shell, AGIP or OMV, alternative hypothesis is dependence. It depends, yes? So we will run this hypothesis test. I will show this on the whiteboard. Okay, so this is the beginning of the table, yes, where we have only these two values, yes. I already said that our zero hypothesis will be mu for the first group is equal to mu for the second group, and this is equal to mu of the third group, yes? Equality of three means equality of three consumptions, equality of consumption of three different types of petrol, yes? So we know that n sample size is 3 times 5 equal to 15, and k number of groups, yes, because we have Shell, AGIP and OMV is equal to 3, yes, so we know this, and there was written that we should use alpha equal to 0.055% significance level. Yes, so this is very important, this value is very important, this value is very important, and this value is very important. Okay, so we will continue here, because we know that sum of squares total is equal to sum of squares treatment plus sum of squares error. Yes, we will calculate treatment sum of squares like simple difference between total and error. Yes, I remember that we already calculate this because we calculated effect size. Yes, effect size like sum of squares treatment divided by sum of squares total. Yes, sum of squares total 0.25073, and sum of squares treatment will be 0.2507773 minus 0.080280. The result is 0.170493. Okay, so that will be 0.170493. Yes, and the result of effect size, which we already seen on our previous seminar a few weeks ago, divided by 0.2507773, 0.6799. Yeah, so this was effect size. What is next? Next column. Degrees of freedom. This is very important. The degrees of freedom. We have two degrees of freedom, Ni1 and Ni2. Ni1 is k minus 1, Ni2 is n minus k. Yes, do you remember from our formulas? So we know that we have three groups and we have 15 observations. So there will be 3 minus 1 equal to 2, and there will be 15 minus 3 equal to 12. So you know that there will be value 2, there will be value 12. We can write here value 14, yes, but it's useless, yes. We don't need this value for anything. Yes. So this is another column, but the most important is this value degrees of freedom and this value degrees of freedom, and treatment and error sum of squares. Because in the next column, as we have mean squares, which is variance, as I will write here mean squares, which is variance, and there we have treatment variance and error variance. Yes, there it's not necessary to calculate anything. So the value here will be calculated like a ratio, sum of squares and degrees of freedom. So 0.170493 divided by 2 is equal to 0.0852 Okay, and here this will be very small number, because you can see 0.08 divided by 12, yes. Okay, so 0.080280 divided by 12. Result is 6.69 exponent minus 3. Yes, 6.69 exponent minus 3, so 0.00669. Okay, so we have here two variances, treatment variance and error variance. And F value of F statistic, F value will be calculated here, and you know that there is nothing over here, yes? So the ratio of these two variances, so 0.0852465 divided by this result, and F value at statistic is 12.7424. So this is F statistic, yes? So I will delete this, and now I will say to you the secret information why this method is called ANOVA method, analysis of variance, while we have here zero hypothesis designed on equality of three means. Yes, there is equality of three means. Average consumption in case of shell fuel is equal to average consumption of AGIP fuel, and this is equal to average consumption of OLV fuel, yes? And the method is called ANOVA. Why? Because our decision is based on Fisher statistic, Fisher F-test, and you need to calculate ratio of two variances, as treatment and error variance, which can be called between group variance and within group variance. The ratio of between group and within group variance resulting to Fisher statistic, and therefore this is called ANOVA method, analysis of variance, because you need to analyze variance in the statistical sample. Yeah, so this is the reason, this is the response. Okay, so we will finish this example because we know that the zero hypothesis is rejected if we enter to the rejection region W alpha, and this rejection region looks like this. For Fisher, F statistic is valid. If F statistic is higher or equal to critical quantile F1 minus alpha with degrees of freedom μ1 and μ2, yes, we will enter to the rejection region and we must reject zero hypothesis. Okay, do you have your statistical tables with Fisher F distribution? Are you able to find critical quantile? Our F statistic is 12.7424, yes, and we must find critical quantile F 0.95 with degrees of freedom 2 and 12, yes, 2 and 12 degrees of freedom, which we have written here. So please find your tables, yes, check your statistical tables and find this critical value. We are not able to calculate p-value, probability. Yes, we don't have Excel, we don't have formula for this. I know how to solve this. I know how to solve p-value. Yes, but it's not part of your seminar, of your syllabus. Yes. So please wait a second. I will check the tables. You can check the tables. 2 and 12, and this quantile is 3.885. 3.885. This is higher than this critical quantile, so we entered to the rejection region, yes, element. Our F statistic is element of rejection region, so we can reject zero hypothesis at a 5% significance level. Zero hypothesis is rejected, so it's rejected independence. There was written independence. Independence is rejected at the 5% significance level. It depends. The consumption depends on the type of petrol. We calculated effect size, so we know the strength of this dependence. We will finish our today's seminar with this example, which again you already know, as this is our situation about monthly expenditures on the household and the number of members in this household. Yes, we already calculated this example manually on the whiteboard. Yes. So because we already know how to solve this example manually, so the calculation of parameters of regression line, B0 and B1, yes, intercept and the slope, I solved this for you in Microsoft Excel now, yes. So suppose that we receive data from this household about the number of members in the household and their monthly expenditures in thousands Norwegian crowns. We will calculate in Excel parameters of the regression line that is describing the dependence of the monthly expenditures on the number of members in the household. We will speak one more time about the value of regression coefficients, and at 5% significance level we will test the slope using hypothesis test of regression parameter. So what is the most important now? We will check our formulas and we will find here these two tables. Yes, you can see that these two tables are practically similar, absolutely similar. Hypothesis test of slope, partial t-test of slope. There is again hypothesis test of slope, partial t-test of slope, but only one difference is that we have x variable in the first table and t like time variable in the case of second table, yes? But everything is same, yes? The slope is slope. So we will calculate the parameters, we will estimate the parameters in Excel, and after we will use this hypothesis test. What's written here? Coefficient is equal to 0. This is zero hypothesis, yes? So we will estimate some coefficient, some parameter of the regression model, yes? And there will be hypothesis claiming that coefficient is 0. What it means? This coefficient is not statistically significant, yes? This coefficient is not statistically significant. What it means? It means that it's wrong, yes? We need to have statistically significant coefficient of the regression model, yes? It's important for us. So our wish is to reject zero hypothesis because alternative hypothesis claims that coefficient beta is not equal to 0, is different from 0, yes? Coefficient beta is, for example, 43 minus 0.5, but it's not 0, it's significant, yes? Alternative hypothesis means that coefficient is significant. We are using test statistic with t-distribution, student t-test, yes? Partial t-test of slope, so t-test, student t-test. T-test is calculated very easy, like a ratio of coefficient and the standard error. There you have written that standard errors of estimate are calculated in software, not only in Excel, in any other software in the world, yes? So if we are using any statistical software in the world, this software will provide to you measures of quality of your estimate, of your parameter. So we know the value of parameter, we know standard error, yes, and the ratio of value of parameter and standard error is student t-test. And finally, because we are using both side alternative, higher or smaller, not equal, yes, higher than 0 or smaller than 0, so two-sided alternative, there is absolute value of t-test. If absolute value of test statistic is higher than critical quantile from t-distribution, 1 minus alpha divided by 2, yes, 1 minus alpha divided by 2, if absolute value of your t-test is higher than this quantile, we will enter to rejection region and we can reject zero hypothesis. So this is our wish. Yes, we would like to reject zero hypothesis. So we know how to calculate B, the coefficient manually, yes, B0 and B1. This is designed for B1, as the slope. So we will solve the slope in Excel, and after we will continue with calculated standard errors. Yes, because you have written here only from Excel, but this word you can rename for any other software, because in any other software you have also standard errors. It's a rule. Yes. Okay, so we will solve this. At the beginning of our today's seminar, we already installed a special add-in, data analysis of data leaf. So please select data analysis, and we will find regression. Where is regression? Here. Please select regression, okay. and you can see that we have here input y range and input x range, yes. I hope that you already know, yes, what is y, what is x, and how to put these values to this table. So today I will select this also with labels, yes. So expenditures are values for input y range, input x range, number of members, yes. I selected labels, confidence level 95%, it means that we are using 5% alpha. So please click on OK. The least squares method will calculate the coefficients, okay, and also the standard errors, yes, the standard errors of our estimate. So I will use only wait a second, 3 decimals, yes, 3 decimals, and the important information for us will be this, because there is the slope of the regression line. Do you remember our regression line about the development, yes, of expenditures and the number of members? We had regression line. I will write it here, yes, for you. So recapitulation: y is equal to intercept 1.333. Wait a second. I don't have selected numerical keyboard. So now y is equal to 1.333 plus 3.714 x, yes. So this is my regression line. Yes, do you remember this? 1,333 Norwegian crowns. The autonomous expenditure, which must be paid even if the house is empty, yes. And 3.714, 3,714 Norwegian crowns, yes, which you need for every other person in your household, yes. So this is our regression line, and now we would like to test this slope, the significance of this slope, yes. So what's important for us? We need B1. So B1 is equal to this value, yes. Wait a second, okay, so this is our B1, and standard error as B1 calculated from Excel, yes, is this value, yes. Okay, so we have everything for the calculation of this ratio B1 and SB1. Maybe you already seen in the previous table the value of the statistic T. It's calculated here, yes, and its value was 11 point something. Am I right? 11 point something. Check this table. Yes, it's here. As you can see, 11.053. So the value of T, value of statistic T, can be calculated like ratio this and this. Yes, 3.714 and 0.336 will be equal to 11.053. Yes. Okay, so I will decrease decimals, and you can see that we have here the same result, yes. And what is important for us now? To compare the t-test, compare the t-statistic, absolute value absolute value of the statistic with t 1 minus alpha divided by 2. Alpha is 5%. 5% significance level. So 5% divided by 2 is 2.5%. 100 minus 2.5% is 97.5%. So please, we will find quantile, student T, critical quantile, 97.5% with degrees of freedom, n minus p, p is number of betas. You have written here that p is equal to 2 in your situation. We have intercept and slope, 2 betas in the model, yes, 2 betas. So number of observation minus 2. How many observation we have? How many observation we have? Please check this 6. So 6 minus 2 is equal to 4. Yes. So we will find 4 degrees of freedom, student T distribution, and I will find, so this is T value, and there will be T critical, bold, and in tables there is Fisher distribution. I must scroll up here. T distribution, P value 0.975, and this is 4 degrees of freedom. 1, 2, 3, 4, 1, 2, 3, 4. Yeah? So 6 minus 2 is equal to 4 degrees of freedom. P value here 2.776. This is a critical value. 2.776. 2.776. I will write it here. 2.77. 2.776. Okay. So there is our final decision. If absolute value of your t-test is higher than critical quantile, we can reject zero hypothesis at the 5% significance level. This is true. Therefore, zero hypothesis, which claimed that this coefficient 3.714 is equal to 0, is rejected. So we calculated, we proved that this coefficient, this parameter of slope, is statistically significant at the 5% significance level. We have statistically significant regression slope. Yes. So we tested the slope using the hypothesis test of regression parameters. Assess the quality of the model using coefficient of determination. We already calculated coefficient of determination. For example, here is already calculated for us. Yes, and you can see 96.83%. Yeah, so it's very high, very close to 1. So therefore, we explained a lot of variability. Okay, so that's all for today. Next week we will continue, we will finish hypothesis tests, and after there is small final chapter about index number analysis. So I will prepare some examples for you for index number analysis. You will see that it's not difficult, a lot of formulas, but very simple and very easy calculations. Yes? So that's all for today. This is the end of our 12th seminar. Next week I will see you for the last time. Yes? We will finish everything. So that's all. Have a nice day, and I hope that I will see you next week. So bye bye.